Thank you. I'll begin with a word of prayer. Heavenly Father, we thank you for the break just completed. I just pray you be with us this week. Help us to glorify you, Lord, in the time that we have that's remaining. I pray that you help the students to just do their best at all the various tasks they've been assigned. I know there's a lot to do in this time that remains, but I know that you can be glorified, Lord, in what they do. In your name I pray, Lord Jesus. Amen. All right, so we talked about Stokes Theorem and also the Divergence Theorem. Let me state those for you again. Talk about them. What they do, what they don't do, et cetera, et cetera. So both of these are theorems which say something about the integral of a vector field. And they both involve differentiation. So I'll start with Stokes' theorem. Stokes' theorem states that for the integral over a surface, let's say S, if you have, and that surface I'm assuming is simply connected, basically meaning the surface doesn't have holes, then the flux of the curl of a vector field is equal to the circulation of the vector field around the consistently oriented boundary of the surface. So the picture is something like this. Let's say, whatever, here's S. And so if the normal to S is like this, the boundary of S, you have to imagine yourself walking along the boundary to give it the positive orientation. Walk on the top of the surface. If you walk on the edge, the surface, the inside of the surface should be in your on your left. So if you can imagine that, the boundary of S has to be like this. Okay, and of course the boundary of S is actually just the edge of it. It's a curve. Now we even talked about before the break, we even talked about the case if S had holes in it, right? You can actually still write the same theorem, but what's the understanding? If there's also a hole, how does same formula, but then if there's a hole in it, then if there was like a hole like here, right? And so S was in between the outer boundary and the inner boundary. So the inner boundary, if you were to imagine yourself a little person there walking along, if you're walking along the edge of the hole, in order to keep the inside of the surface on your left, which way would you have to walk? My picture, you'd have to walk, kind of the opposite way. So this would be the boundary of S here. Yeah. So if the red outer edge is counterclockwise, then the inner edge would be clockwise, for example. And no, okay. Of course, if you have that the curl of F is 0, right, between the inner and the outer edge, then you would get that the line integral along the inner edge is equal to the line integral around the outer edge. You get a curved version of the deformation theorem as well here. This is Stokes' theorem, with or without holes. Now, the divergence theorem states the following. It states that the flux, I'm going to state it in kind of I'm going to flip it over here, comparatively speaking. The divergence over the boundary of, say, some solid region, we call it E, script E, all right, of a vector field F dot ds. So the flux of the vector field through some surface. Now this surface, I'm assuming this is the boundary of a simple solid. What's a simple solid? Like cheddar cheese, simple solid. Swiss cheese, not a simple solid. It's got holes in it, right? So this is equal to the triple integral over the solid region itself, E, of the divergence of f dv. So the picture for this is kind of boring. I mean, whatever, it's some kind of three-dimensional solid, and I'm assuming that the normal to the surface is outward oriented. So it has to be positively oriented. Otherwise, you put minus in. And then, just, so for example, this could be a ball, and this could be the edge of the ball, what we usually call a spherical shell, or sometimes just a sphere. There's always a certain ambiguity when somebody says sphere in this kind of class, whether they mean the solid sphere or if they mean just the spherical shell. You should always be wary of that distinction. And don't be afraid to ask your professor about which one they mean. Sometimes they just haven't said it in such a way that it communicates to you. That's not usually what we're trying to trip you up on. Okay, and anyway, is there a version of the, this is the divergence theorem, also known as Gauss's theorem. Is there a, can you do this? Can you put holes in this theorem? Like, what if there was a hole? So let's talk about that. Extending divergence theorem to solids with holes. I'll start out with a single hole. So here's a picture. I'll draw a sphere, and then you can imagine that there's some kind of inner void. Now, I have a hard time understanding this picture, so I usually like to draw something like, I don't know, just kind of like imagine cutting in half, right? And so inside there's, I still can't draw it with anything. So, all right, I'm trying. This is the picture missing from my notes. I think you see why. There, it's starting to get kind of better. Here's one half of it. There. So you imagine the other half, right? Now, so think of this as being E, right? So, and fine. Sorry, I had to get this out of my system here. Whatever. All right, so there's this hole, right, that we're imagining. Now, if you took this solid that has a hole in it, do you see what you could do to it to make it into two simple solids? What would you do? Yeah, just same thing we've been doing on like every one of these silly theorems. We just chop it like that, right? Right, and then so like this. Oh, that's not really. I mean, this isn't really an edge of it, is it? That's just where it's joined. Right. So you can imagine, I mean, you'd have basically just say E top, right? And you can imagine that you can cut it, right? And the other half you could call the base or whatever. And you see what happens is that the boundary of the top unioned with the boundary of the base is what? It's the boundary of the whole thing provided what? Yeah, I'm assuming that the top piece and the bottom piece are both positively oriented, right? Which means that they have the normal vectors looks like this, right? So down here, and so forth, right? Inside the hole, like that, right? For the base, it would be like this, the normal vectors, but then they would be upward pointing on the lower half of the hole, right? And then on the face, these would be. So you see that the place where we did the cut of the solid, the flux from the top piece and the flux from the bottom piece, they're equal and opposite. They would cancel out if you add these, right? And you see that giving the top piece and the bottom piece positive orientation implies that the natural orientation for the solid with a hole in it is that the outer skin has an outward orientation, right? But the inner skin, if you will, the surface to the whole of it, that has to be inward pointing normals, right? So this is, when I write this, I'm advocating a definition where we define the normal to point away, or let's just say outside E. I mean, that covers both cases. The normal's always pointing outside E. Right? Actually, if you look at the normal vector itself, it's not pointing into the surface. Now that does, I mean, we should understand it, a vector of sufficiently short length. I understand you could come up with some kind of weird looking genetically modified bean or whatever, like this kind of thing, where you might have a normal vector that pointed like that and like that, and they might like intersect the surface somewhere else, but think of short normal vectors if you had some kind of malevolent surface like this. Okay, anyway. With this said, if you just apply Gauss's theorem to the top piece and apply Gauss's theorem to the base piece, you again get, the divergence theorem in total, where we have the net flux is it's the flux going out of the outer and the flux going into the inner. And also if the divergence is zero, right? If the divergence is zero inside the region with a hole, we get another kind of deformation theorem. We get that the flux is the same in the inside to the outside, right? Like here, let me show you an application of this. So we have previously calculated, if you look at the vector field F equals to 1 over rho squared rho hat, right? So this is the Coulomb, so-called Coulomb field. And we have previously calculated that the integral, the flux of that, right, over, say, the sphere of radius 1, we've shown that that's 4 pi. Here, I'll work it out again. Integral from 0 to pi, integral from 0 to 2 pi, 1 over rho squared rho hat. The surface area element for a sphere is rho squared sine phi d theta d phi in my current notation, but also we have rho is equal to 1. I mean, they cancel anyway, but these actually are 1 and 1, so there's a rho hat here, I forgot. So you take the dot product, un momento. All right. Take the dot product of rho hat with rho hat. You get 1. either you cancel the row squareds, they cancel out, or you plug in rho equals to 1. Anyway, you're left with the integral from 0 to pi, sine phi d phi, integral from 0 to 2 pi d theta. What you got? You got 2, and you got 2 pi, you got 4 pi. We have also worked out that the divergence of this vector field is 0. The divergence of 1 over rho squared rho hat is equal to 0 for rho not equal to 0. Not an entirely trivial calculation, but it's one we can do. All right? So, consider this then. Here is the sphere of radius 1. I'm just going to draw it kind of like a two-dimensional version of it. You can imagine these things kind of bubbling into and out of the board. And then, I don't know, take any simple surface that you like. Any surface without holes which is outside the sphere of radius 1. It doesn't matter what it looks like. Okay? So if I mean, this is just the two-dimensional slice of it. The real picture is something like, you know, you've got the inner sphere, and then there's some kind of like blarby. I can't even draw it. I mean, imagine a mess of jello with a smooth edge that's surrounding this sphere. What's the flux through the green? So I'll call this S2. Well, we can apply this theorem that says that the integral, let's say that E has boundary of E equal to, minus S1. I call it SR equals to 1 at the moment, unioned with S2. Why minus? Because this, what do we do here? Outward pointing normal, right? So the integral over E of the divergence of f is equal to the integral, well, the double integral over minus SR equals to 1 of f dot d ds plus the integral over S2 of f dot ds, right? And, okay, this is 0. Because by the way, while in the inside, a point which is actually not actually part of the point set E, the origin, right? Like that's here, right? That's a problem point for this vector field, this Coulomb field. The Coulomb field diverges at that point, right? But that's not a problem because that point's not actually in E as a point set. I mean, geometrically, it's inside here, but I would say that that's outside of E, all right? So it's like if you're talking about a house, perhaps, you could actually talk about I don't know. It'd be something like saying something's only in the house if it's in the walls themselves, as opposed to if they're in the rooms, they're not really in the house. So the usage here of the word in is very careful. I'm saying the origin is not part of the point set E, right? It's inside the inner edge. Okay, anyway, so that's 0. This is minus 4 pi, so therefore the integral over S2 of f dot ds is equal to 4 pi. which is pretty awesome because that's an arbitrary surface, right? What does it say about this Coulomb field? That says this Coulomb field, the flux of the Coulomb field is completely coming from the origin. I keep coming back to this example because it's an important example for you guys to really, really understand. Right? It's not that I forgot that I did it the other day. I'm really doing this on purpose. If this is like the first time you've seen this example, you really have not been paying attention in here. Sorry. What's that? Yeah, what happened to the t-shirt is a good question. It's right here. Don't worry. Okay, so hey, let's look at a different example where the divergence is look at another example of the divergence theorem. I like this example. Well, there's an example in my notes with a staircase, which I think is really kind of amazing. Fine, I'll do it. Suppose you have f of xyz equal to x y plus z y cubed z. Find flux of f through outward oriented staircase. So here's the staircase I have in mind. Sure. Oh. Yeah, I meant plus c. Sorry about that. Now, let's see here. This staircase, I'll make it relatively simple, as staircases go. Let's suppose that this point is like 3, 3, 0. This point here is 0, 3, 0. This point is 0, 3, 1. This point is like 0, 2, 2. This point up here, 0, 0, 3, 3, 0. You get the idea? So basically, I'm describing a staircase that is 3 units. It's a width of 3, right? And each step is 1 unit deep and 1 unit high. Now, now I said calculate the flux through the staircase. What would be, if you were going to calculate this directly, what would be required of you here? Like a very evil teacher would ask you something like, verify the divergence theorem for this staircase. Like, if you see the word verify in a homework problem for either the divergence or the Stokes theorem, you should realize that those are mean problems. I probably did one of those to you. But, I mean, it's kind of like, okay, verify, fine. Verify means you calculate both sides independent of each other and show that they work, show that it works. That's what it means to verify the theorem, right? But, I mean, here you'd have the like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 separate, by my count, surfaces to calculate the flux through. Ugh, it's unpleasant, right? Or you can use Gauss's theorem, or the divergence theorem, which says, I need to give this staircase a name. I'm going to call it E. Okay, so the solid staircase is E. So the boundary of E is what we're asked about. Calculate the flux through that of, x, y plus z, y cubed plus z dot ds. Okay, great. I love the divergence theorem. because I like volume integrals. Volume integrals are nice, comparatively speaking. What's the divergence of that vector field? I could have made this problem look even worse, right? I could have easily thrown in, like, you know, some random function of x, like, you know, the fifth root of x to the fourth plus x squared minus 77. I could have done that, or something like that. It wouldn't have changed anything, because the divergence only picks up on what? Partial x, partial x, plus partial x, partial y rather, of y plus z, right? Plus partial z of y cubed plus z. That's the divergence, and of course that's what? 3. Okay, so what we have is 3 times the volume of E is the answer. What's the volume of this staircase? You don't need to do integration for that, right? You need 3 plus 6 plus 9. See, this one has 3, this one has 6, this one has 9. 1 by 1 by 3, 1 by 2 by 3, 3 by 1 by 3. 18 times 3. What do you got, 54? What? 54? Okay, good. This vector field is very different than the Coulomb field, right? This vector field is everywhere diverging. If we think back about field lines, its field lines are being created everywhere in space. The more volume you enclose, the larger the divergence. It's really hard to, it's easy to picture this one. Where are the field lines coming from? They're coming from the origin. They just go out like that. So whatever line cut through the inner circle, you know what? It cuts through the outer surface just the same. And the number of field lines is conserved because the divergence is everywhere 0. So whatever field lines you start with at the origin, they just spread out. That's the Coulomb field. This thing is very different. You can see it in the formula, right? The magnitude of F is just growing to infinity in every direction. The magnitude of the Coulomb field, it's going to 0 as rho goes to infinity. But it does such a way that it's balanced as, if you consider a sphere, as it goes to infinity, the surface area gets larger and larger, right? At the same time, the magnitude of the field gets smaller and smaller, but they do in such a way that the flux remains 4 pi for that weighting. Any questions? Yeah.
Short thing. If F would have been the Coulomb field for this, it would have just been 1/4 pi, right?
Oh.
I'm sorry, 1/2 pi.
What would where do you have in mind? You're thinking the Coulomb field with the usual one, right? Like the.
Yeah, at the origin.
So here's the origin. What's the flux through that? You know, yeah, the flux should be, it should be pi over 2. Because I can think about, I mean, it's easy enough to see that if you change this, that's an interesting comment, Luke. That's a new kind of problem for me. If I extend the staircase to the cube like this, right, the divergence between the staircase and the solid cube is 0. So the flux through the staircase and the flux through the purple cube, or let me make it red. The flux through the red cube, they're equal because the divergence is 0 between these two surfaces. I can apply the deformation theorem basically. And then I use the symmetry argument. See, this is 1/8 of the, if you think about the big cube, not to scale with the other picture, right? So this is the origin. And so there's like this upper octant. That's 1/8 of the total. Well, I shouldn't think about volume though. I should think about surface area. Is that 1/8 of the total surface area as well? It's like 3/4 of a face. I mean, it's got this face and this face. It's still okay. Cool. All right. Well, it's still 1/8 of the total surface area. It's just that. Curious. Let's see here. No Mr. Vu. Man. Try to give stuff back. Patrick here. No. I would have noticed Zach. Let's see here. James. No. All right. I have, a couple big applications just for a second here before I get off the beaten track too much with an actual example. One of the main uses of, so over here, I'll start with the divergence theorem. In electromagnetism, we learned that the divergence of the electric field is equal to rho over epsilon naught. So here, that's a different rho, unfortunately. Here, rho is equal to dq dv. It's the charge per unit volume. So if I integrate this, over some volume, right? I'll pull the constant epsilon naught out front. What's the integral of rho dv over the volume then? If rho is dq dv, what's rho dv? It's just dq, right? What's the integral of dq over the volume? Q, it's the charge enclosed in the volume. So this gives us q enclosed over epsilon naught. On the other side, the divergence theorem, or Gauss's theorem, gives us that this is the flux of the electric field over the boundary of the volume. And there you go. That's Gauss's law that we use and torture the students with in Physics 232. There it is in all of its glory. Now, what I started with is the local version of Gauss's law. This is Gauss's law as a differential equation. That's the local expression of Gauss's law. In my view, this is more fundamental. Okay, now to explain what Stokes theorem has to do with physics, it's more complicated, but there is this relation that the curl of the magnetic field is mu naught times, mu naught times J. Now here J is equal to current density. So if you integrate the curl of B, and this I'm thinking of the so-called magnetostatic case. which means that the currents that are involved are long, steady currents, like a DC circuit. All right. Then the curl of B along, the flux of the curl of B along the boundary, along some surface, right, will be equal to, well, let's see here. This is so-called, what I'm writing here, this is known as Amperes Law. All right. Technically, it's Amperes Law without Maxwell's correction. I talked about Maxwell's correction a little bit some other day, where we derived the wave equation for light. But if we're in the situation of magnetostatics, then we don't have that correction term. So we just have this. And the J was 0 in the thing we did before, because we considered these equations in free space. But anyway, in the vacuum. So this would be the surface integral. I'll pull the mu naught out. And we have the surface integral of J dot ds over S. So you could picture it something like this. Here's my surface, right? And here's the current going through, right? Now, J is current density. Specifically, it's current per unit area. And it's a vector because it points in the direction in which the current's going. If you integrate that, the flux of the current density is exactly the so-called current enclosed by S. It's the current which is actually cutting through the surface directly. So current which goes tangent to the surface, S doesn't count. Current which cuts perpendicularly through it counts directly. Does that make sense? So if you just had a single wire, a physical wire that had like 1 amp, and it was just going through the surface like straight up normal to the surface, and if the surface had like 2 meters squared area, the J would, well, who cares what the area is? Anyway, the integral of J dot ds would just be, 1 amp, whatever the current was through that wire. Okay, on the other side, Stokes theorem says that this is what? Integral over the boundary of S of B dot dl.
You said B dot dl for B dot dr.
Yeah, I meant dr. Sometimes I write dl for line integrals in other places. Like the notation B dot dr is not sacrosanct. There's other notations used other places. In physics, it's often the case that we'll write instead of B dot dr. It has the same meaning. Oh, and there you go. This is the so-called Amperes Law. For example, if I had a single current flowing up like this, I, and I take a circle, say of radius r, away from the current, and I apply this thing we just worked through, I get that if I ask what's the magnetic field out here generated by the current I, Amperes law says it's the integral, the circulation of the magnetic field around this loop, let me call it C, is equal to mu naught times I. The current enclosed by that loop is just I, right? But by the symmetry here, the symmetry is that the magnetic field has to point exactly parallel to the curve. So this line integral just gives us 2 pi RB equals to mu naught I. And lo and behold, here you get the standard formula we like to use, mu naught I over 2 pi r. There's the magnetic field for a very long wire with a steady current, the magnitude of the magnetic field, a distance r away from the axis along the currents flowing. So, the divergence theorem and Gauss's, the Stokes theorem, very important to electrostatics and magnetostatics and also the non-static case, because they link the flux and the line integral and the volume integral in this way. And because of the way the electric and magnetic fields are related to moving currents and charges, this allows us to find, the values of the electric and magnetic fields. This is what Physics 232 is about, but, it's more than that. How much time do I got? 7 minutes. All right, good. Let's see here. Number 2. This is Cully's vector calculus. It doesn't really matter. It's first edition. You probably can get it for $1. Anyway, so we've got a surface, and it is parametrized by x of st equal to s cosine t, s sine t, and t. And this is for the parameter ranges 0 less than or equal to s less than or equal to 1, and 0 less than or equal to t less than or equal to pi over 2. We're asked to verify Stokes Theorem for the given surface and vector field. So there's the surface. The vector field we're given is f is equal to, I'll put into my bracket notation, z x y. Okay, by the way, you guys would see this written something like this. A lot of other places, right? But they're usually bold. IJK, I don't know how to write bold on the whiteboard, so I just kind of gravitate towards this other way of thinking. Okay, so to verify Stokes' theorem, what do we do? I guess first we need to understand what this surface is. What is this surface? It's a cylinder. X squared plus y squared is equal to s squared. Is s squared equal to t squared? It's a helix. It's a helix which, yeah, this is kind of like, it's the union. Okay, so like s equal to 0, what do you get? Right, so we get from 0 to 0 to 0, 0, pi over 2, right? That's s equals to 0, is that line, that ruling. And then, if you think about s equal to 1, you get some kind of like, yeah. And then, if you think about s equal to 1, s equal to a little bit more than 0, s equal to half, you get like that, like that. I mean, it's that's not a very good picture of it. This is part of what's known as a helicoid. It's formed from sort of pasting together a bunch of helices. Now, okay, so what's the boundary? Wow, that is a nice problem. What's the boundary of S? I think it's helpful to think about what this is, right? S goes, so if this is S and this is T, we're basically just mapping like this rectangle, right? This is what X does, is it takes this flat rectangle in the TS plane and it maps it to this helicoid thing. Now I think we can understand each one of these edges by a certain thing. Like, let me do it in color. This edge here is what? that would be what? That would be t equal to 0, right? Right, s ranges from 0 out to 1. And then let's see here. I can also look at this piece here. Let me call that 2. 2, we have s is equal to 0. 0 less than or equal to t less than or equal to pi over 2. The third thing I see, like this piece up here, right? So 3, what do we have there? We have t is fixed at pi over 2 and 0, right? That's that piece. And then the outer edge of this portion of the helicoid. 4, we would have, well, we have s fixed at 1. Okay, so what, and now what, as we should like for them to be oriented like 1 is the right direction, right? To be positively oriented, I really need like this, right? I need like that, and I actually need 2 to go the opposite way, right? If I'm assuming that, well, I don't know, I don't have to, well, I'm not sure I need to yet. So let's take the curl of f. What do we got? What on earth was that? See here, so 1, 1, 1, okay. And what's the normal to this helicoid? It would be partial x, partial s, right? Across partial x, partial t, which is going to be the determinant of x hat, y hat, z hat of what? Partial x, partial s is cosine t, sine t 0. Partial x, partial t is minus s sine t, s cosine t, 1. So what's the normal here? Looks like we got sine t minus cosine t. S. Is this perpendicular to both of these? It's a quick check. Yes. And then so to calculate the flux of the curl directly, we have to do what? We have to integrate from 0 to 1, integrate from 0 to pi over 2. The curl of f was just what? 1, 1, 1, right? If you don't mind, I'm just going to go ahead and take this dot product. Can I do that? So here's the curl of f is this, right? ds is n ds dt, all right? And here's the n right there. So when I take the dot product of those two things, what do I get? I get sine t minus cosine t plus s, and dt. ds, what's that integral give me? Well, the ds is easy. That just integrates to nothing, right? So I got myself a minus cosine t evaluated from 0 to pi over 2, minus sine t evaluated from 0 to pi over 2, and oh, excuse me, I can't just integrate the s to nothing on this term. This term does the what? The s integrates to what? 1/2 times pi over 2. Do you agree? That s term, 1/2 is the s integral, and then pi over 2 is the t integral. I'm just doing that separate. What's that? Yeah, integral's additive. So this gives me 1 minus 1. Answer's pi over 4. Of course, that's only half the answer, because now what do we have to do? Remember I said verify questions are mean? So in order to verify this, what would we now have to do? We have to calculate the line integral over this piece, this piece, this piece, and this piece, add them together, accounting for the orientations, and hopefully we get back to pi over 4. I mean, this showcases why Stokes Theorem is such a nice theorem, right? Because to actually calculate the line integral of f over the edge of this helicoid, it's rather nasty. The curl looks scary, but it's actually way easier to calculate the surface integral of the curl as opposed to explicitly calculating these 4. I don't think I have time to calculate these 4 today. And by tomorrow I'll have forgotten about it, so sorry about that. Maybe you can do it on the test. No? All right, Andrew, do your thing. Go ahead.